Hello, folks. Welcome to Chapter 4, Lecture number 3. I'm going to talk today and explain one of very interesting phenomenon in high voltage engineering, the streamer mechanism, or what is streamer breakdown mechanism. People call it streamer discharge also. People do call it streamer, but let me tell you, I've come across in my life, not everybody exactly understands the streamer mechanism. I'll explain it to you. It was by virtue of the hard work by the scientist Rather, I did mention, I think, in the last lecture, and he has given exact definition of streamer breakdown mechanism. In the last lecture, we talked about Townsend's theory and the breakdown mechanism given by Townsend, and the criterion for a breakdown mechanism we had as Townsend derived. It was gamma e to the power of alpha d. When this is equal to 1, this is given as criterion for the breakdown mechanism given by Townsend. Now, the validity of this mechanism of breakdown, all the work in atmospheric air, but people have done later on carbon dioxide, nitrogen, helium, other gases too. So this criterion, if it is met, Townsend mentioned it to be this was known later by Townsend to the world, Townsend's mechanism, and he did his work in 1914, more than 100 years back. So, but one very important thing here is that Townsend performed his experimental investigations on uniform electrode system with a very small gap distance. He did not perform the experimental investigation for more than 4 centimeters. Just imagine, very small gap distance. So it has found some limitations. Later, when the measurements were done, it has found some limitations. But let's first describe how has Townsend described his mechanism. As we did talk about, because of when the field intensity is high, the ions strike back on the cathode, as you can see in this slide on figure A. Ejection of electrons from the cathode. When the metastables and ions strike back on the cathode, they eject an electron. The whole process has to begin, the avalanche process has to begin with an initiatory electron, which must be made to be available in the dielectric at the cathode. Further, when the single avalanche begins, it leaves behind the metastables and ions at the back, and these are heavier particles. They strike back on the cathode, and then from the cathode an electron is ejected out. Every electron ejected out from the cathode, we have learned that is the gamma process, gives rise to another avalanche, and that is how number of avalanches are produced. Within the avalanche, the alpha process multiplies the charged particles, or results in exponential growth of charged particles within the avalanche by alpha process, and newer avalanches are produced by the gamma process. As you see in the figure B, generation of series of avalanches on the cathode takes place. That is how he described it to be. And in figure C, building of positive space charge near anode after 4 generations of the production of avalanches. I mean, it takes time for positive space charge to get built up at the positive space charge to be built up at the anode, and after 4 generations. And then what happens? Breakdown. These avalanches constriction is a very rightly word used here. That means they join up into a single channel. Number of avalanches join together to form a single breakdown channel. And by the time the positive space charge is just given rise, the breakdown takes place. That is how the Townsend has described this mechanism. This is just a schematic diagram which Townsend had given, which I have also drawn further. Now what happened is that Townsend performed his experiment, as I said, not greater than 4 centimeter in uniform field. And that is how the mechanism described by Townsend is valid only for small gap distances in uniform field. Now, with this theory, you would appreciate if you try to calculate or measure the time required for breakdown after applying maybe a pulse voltage of required magnitude. The time required or time taken from the initiation of a single avalanche to the accomplishment of the breakdown is calculated in this through this theory is the time required by the drift velocity of electrons. That means the drift velocity of electron at the cathode, how much time it takes to reach the anode, and that determines the total time required by the for the breakdown. But when the experimental investigations on slightly longer gap distances were performed by other scientists, they found that the time required, in the meantime, after Townsend, the instrumentation techniques also improved. So they found that the time required for achieving the breakdown is much shorter than the drift velocity of the electron. That means the drift velocity of the electron takes much longer time to travel for the electron from cathode to anode. But the breakdown is accomplished in a shorter time. That perplexed the other scientists. What is the reason behind? So the experimental, as I said, in high voltage engineering, experimentation takes first and results are then interpreted into theory, I'm to say mathematically. So this perplexed the total time required for the development of the breakdown channel or the discharge process for accomplishing the complete breakdown between the electrodes. this was when people started working at a longer gap distance than, mm, than at longer gap distances, you can say. The time required was much shorter than the time it would have required for an electron to move from cathode to the anode, that with its own drift velocity. This was discovered by Rayther. So, uh, yeah, that means if the spark breakdown, we also call it in gaseous dielectrics, when breakdown occurs, we would have called it to be spark breakdown. When the spark breakdown begins with a single avalanche, the time required was much shorter than the time required for an electron to travel between the cathode and the anode. Now, what happens that when you take a longer gap distance, you can imagine the size of the avalanche to be able to develop in the gap would also increase. When the size of the avalanche increases within the gap, the number of an avalanche contains a number of charged particles. That is, you can say in one way, the number of ions at the tail of the avalanche and at the head of the avalanche, the electrons, and the number of charged particles, that is ions as well as electrons, also increases. And since the number of charged particles segregate themselves, positive ions at the back and negative electrons in the front, they might make a cluster. And we had described what is a space charge. Space charge is nothing but accumulation of like polarity charge. So the space charge is able to develop around because of the avalanche increasing its own number of charged particles. So positive space charge at the back and the negative space charge at the front develops in the avalanches which are of greater length, that means a larger avalanche. So the Townsend theory was not able to explain this. Rayther performed its experimental work and then gave, when the breakdown takes place with an avalanche of above a certain magnitude, it can be described with the number of charged particles or the length of the avalanche. The mechanism is different. The mechanism is called to be streamer mechanism. Now he derived equations and tried to find out what is that number of charged particles which distinguish between the breakdown mechanism given by Townsend and beyond that, where the charged particles are more, when the avalanches of bigger size take place, what actually happens. So transformation from avalanche to streamer process, the first was said, the Townsend's mechanism was said to be just avalanche process, although both of them involve avalanche, but avalanches of different characteristics. That is very important. So the transformation from avalanche to streamer process began to develop from the head of an electron avalanche when, mind it, the number of charge carriers increased near a critical value. Number of charge carriers within the avalanche increased near a critical value. And that critical value was calculated if the avalanches begin with n naught, as we have already talked about. E to the power of alpha xc is equal to 10 to the power of 8. That's the total number of charged particles in the avalanche work out to be 10 to the power of 8 avalanches. Sorry, 10 to the power of 8 charged particles. For an avalanche initiated, let's talk, suppose if you are able to perform an experiment that there is only one avalanche, that is avalanche initiated by a single electron, and naught is equal to 1. If you put the value of n naught to be equal to 1 in a uniform field, this corresponds to the value alpha xc is equal to alpha dc. This alpha xc, c suffix is given for the critical length of the avalanche. That is critical length up to which the avalanche is extending, or you can say, let's say, with this, what is the critical gap distance above which the different process will take place, that is dc. And when we equate this equation, alpha xc is equal to alpha dc is equal to 10, the natural logarithmic of 10 to the power 8, the value of alpha xc or alpha dc works out to be 18.4. Very simple. On the basis of experimental results and some simple assumptions, Rather, that was in 1939, developed the following empirical formula. As you can see, this for streamer breakdown criteria. For just 1 minute, yeah, 1939 it was. The streamer came up with a criterion for breakdown in uniform field, obviously. Here a new electric field is taken into consideration. EA, as you see it here, EA is taken into consideration, and A is for avalanche. You can imagine when the avalanche carries a very large number of charged particles, accumulation of charged particles, we said, is a space charge. But whenever charged particles accumulate, they form their own electric field. So we have to take into consideration two electric fields in the gap. One, the applied electric field E naught, as you can see it, and the other one, the electric field developed by the avalanche, EA. So alpha xc, he derived this empirical equation. Alpha xc is equal to 17.7 plus ln xc plus ln EA by E naught. And if EA is equal to E naught, this equation will result into alpha xc is equal to 17.7 plus ln xc. What is this condition? EA is equal to E naught. That means the field developed by the avalanche EA is of the order of the applied field intensity in uniform field. So here it is analyzed, the interaction between the two fields. One, E naught, the applied electric field between the two electrodes, and another EA, the electric field developed by the avalanche itself. The interaction between the space charge space charges, that is positive and negative space charges, and the polarities of the electrodes result in distortion of the uniform field. You can say for when an avalanche of above critical amplification is able to grow within the gap, the field between the two electrodes is disturbed and the field intensity is not anymore uniform. So that means it is rendering the field between the two electrodes to be non-uniform. And that is the basic cause of the or basic difference between the two mechanisms, what we are talking, the Townsend and Rather mechanism. Townsend did not experiment for very long gap distances, which Rather accomplished, wondering about the situation after the measurement of the total time required for breakdown. Now, the field intensities towards the head and the tail of avalanche, as you can see towards the head, this is the tail of the avalanche. So the field intensity here, tail, and this is the head of the avalanche. Acquire a magnitude EA. The field intensity at the tail acquire a combined field intensity EA plus E naught. This I might not have talked, but you can learn, given in the book, that when there is opposite polarity fields, that means the positive ions are making here the positive polarity field, whereas it is near the cathode. So when the opposite polarities come together, potential due to opposite polarities come together, the field is enhanced. That means the field at the tail becomes E naught plus EA. At the head of the avalanche, negative space charge is there. Negative polarity field is given rise. Again, with respect to the positive anode and the negative space charge field, again, opposite polarity space charges or the opposite polarities come together and they enhance once again the field. So at the head, as well as at the tail of the avalanche, there is an increase in the field intensity. Whereas in the middle, there is a decrease. Why there is a decrease? Because it's very simple, slightly difficult to understand. The space charge, which one will be stronger, positive or negative? Always the positive space charge developed by ions will be stronger than the negative space charge developed by the electrons. You can understand why. Because they have a difference in their drift velocity of the order of 150 times. So the positive ions being slow, they make a cluster which is more compact as compared to the cluster of negative electron, which is not that compact or is not that dense. So the positive polarity space charge gives rise to a field which is stronger, and that positive polarity with respect to the positive electrode, that is anode, gives rise to a field which reduces proportionately. That means when the like polarity potentials come in contact, the resultant potential or the resultant field is lower, it is lesser, and when the opposite polarity potentials of the charges come together, they enhance the field. So this is a very well-known phenomenon which has been also studied, and if you want, you can study that from the books. So as you can see here, let's talk about, yeah, the minimum value of alpha xc. Xc is the critical amplification of the avalanche required for breakdown in a uniform field by streamer mechanism is obtained on the assumption that the transition from avalanche to streamer, that means the Townsend to streamer Rather process mechanism given by Townsend and Rather, that is the transition from avalanche to streamer occurs when an avalanche of critical size just extends across the gap distance, that is dc. So the minimum value of alpha xc required for breakdown in a uniform field gap by streamer mechanism or for streamer mechanism to be able to take place is obtained on the assumption that the transition from avalanche to streamer process occurs when an avalanche of critical size just extends across the gap distance. That means when the avalanche of sufficient size is able to develop, the space charge starts affecting the field between the two electrodes. That is the main thing. So another field is given rise, and that does happen. That is made assumption that is the critical size of the avalanche is able to grow, which contains the total number of charged particles to be equal to 10 to the power of 8. One thing, and I'm talking here, you would wonder, why am I not talking about the gamma process as given by Townsend? In fact, when the size of the avalanche increases beyond the critical or to the critical amplification, that is 10 to the power of 8 charged particles within the avalanche, the gamma process, that is the cathode effect, is minimized. Why? The cathode effect is valid only for very small gap distances. But when you increase the gap distance, something happens within the air quite away from the cathode, because the potential applied is at the anode. The more development takes place near the cathode or near the anode. So the cathode effect is minimized for longer gap distances, and that is why for Rather mechanism, Rather could imagine, and it is true, that the gamma process does not play a role for longer gap distance. We just make an extreme. Suppose the gap distance is 1 meter. Will the cathode, that is at the ground plate, affect what is happening in the total gap distance and when the potential is applied by the anode 1 meter away? So the gamma process in longer gap distances is not applicable. It was applicable only for very small gap distances. So this is very simple, common sense, and by incorporating this condition, what we just now mentioned, that when the streamer process begins when the avalanches acquire a certain minimum length, that is critical amplification of the avalanche. The criterion for streamer breakdown takes the form alpha dc is equal to 17.7 plus ln xc, because by this time the field developed by the avalanche is of the order of the field applied between the two electrodes in uniform field, and that works out alpha dc to be equal to 10 to the power of 8 as we determined, and which is equal to 18.4 10 to the power of 8, then which is equal to 18.4. For alpha xc is equal to ln 10 to the power of 8, xc works out, that is the critical length of the avalanche, or the length of the avalanche for critical amplification works out to be equal to 2.01 centimeters, or you can say very easily 2 centimeters. Hence, a gap distance of 2 centimeters between the uniform field electrodes can be considered to be the minimum or critical gap distance dc for streamer phenomenon to take place in atmospheric air. Obviously, if you take different gas, it may be slightly different. If you increase the pressure of the gas, it will also vary. But in atmospheric air, under the normal temperature and pressure is also mentioned, it is the minimum critical gap distance between the uniform fields is required to be 2 centimeters. When you increase the gap distance, obviously the streamer process will take place, and below 2 centimeters the Townsend mechanism or the avalanche process would take place to accomplish the breakdown. The streamer breakdown criterion can therefore be interpreted as a condition for the development of significant field distortion. Mind it, the field produced by the space charge of the avalanche produces distortion in the applied electric field caused by stark space charge within a single avalanche, so that its field intensity is comparable to the externally applied field. That means EA is comparable to E naught, then this streamer breakdown criterion is met. Yeah, so streamer described his mechanism in a, Rather described his mechanism, which he gave the name streamer, in this way. So this is when an avalanche, a single avalanche begins at the cathode. That is, primary avalanche electrons swept into the anode. You can see at the anode, the negative electrons would be fast absorbed, and very heavy or very high concentration of like polarity positive ions take place, which gives rise to the field distortion as explained in the previous slide. And because of that field distortion, the field enhancement and field reduction both take place as explained, and there is more of enhancement at the towards the tail of the avalanche. And when the field intensity in the air between the two electrodes increases towards the tail more than the applied electric field, that means E naught plus EA in this region, E naught plus EA is the resultant field. There will be alpha process again here, and there will be newer electrons given rise from the air itself. And when newer electrons are given rise from the gas itself, they begin another avalanche process within the gap, not from the cathode, within the gap. And then the secondary avalanche feed into primary avalanche. What happens? The newer electrons given rise within the gap, they feed the charged particles to the primary electron, to the primary avalanche. Why? The charged particles always acquire the least resistance path, and an avalanche is conducting, so the is not very healthy part of the dielectric, that is air. So the newly developed charged particles start feeding into the primary electrons, which they find the lower resistance path. And more secondary avalanches start feeding into the primary avalanche, and the breakdown is occurred. What is the requirement for breakdown to take place is the generation or production of sufficient number of charged particles within the gap to form a conducting channel in which very large number of charged particles flow. So that is how a self-propagating streamer breakdown develops from a single avalanche, as you can see. Most interesting, I love this figure. This is a photograph. This one is a photograph or explaining the streamer mechanism taken by Rather. You have seen photograph of a single avalanche earlier. That was below critical amplification avalanche. And this photograph has been taken in longer gap distance, accomplishing the breakdown with a single avalanche. When the avalanche grows above critical amplification, the number of charged particles is much higher than 10 to the power of 8. And the space charge, as we learned towards the tail, because of the space charge, total field intensity is enhanced, new avalanches give rise, and they feed into the primary avalanche. So this is your secondary avalanches, and this is your primary avalanche. The secondary avalanches are feeding into the primary avalanche, and the single avalanche acquires more and more charged particles and leads to the breakdown. And this is how the streamer mechanism described. That means for a streamer mechanism, the criterion that the total number of charged particles must be more than 10 to the power of 8 in the avalanche, and that can be accomplished above a certain length, or certain gap length between the two electrodes, and that gap length, the minimum gap length, is 2 centimeters. Above 2 centimeter, streamer mechanism would develop, even in a uniform field, to be able to accomplish the breakdown. I hope I have been able to clarify the streamer criterion for breakdown, and which is a very interesting thing I find, which is not clear to many of the people working in this field of engineering. When we have learnt the mechanism, Townsend's and streamer mechanisms, let's go next to the breakdown. We will learn one by one the breakdown voltage characteristics in uniform fields, Then we later learn breakdown voltage characteristics in weakly non-uniform fields, and then also in extremely non-uniform fields. How do the breakdown, all in air, we'll be talking in air, because I said the maximum amount of work people have done is taking atmospheric air as dielectric, because it is simpler and you can have so many variations and you can perform the experiment to the tune what you like it to be. It's simpler. So a lot of theories, a lot of things have been derived by working uh, on different kinds of fields in atmospheric air. So again, quite long back, this law, Paschen's law, this is again, we call it Paschen, people say, no, it's wrong. It is Paschen's law. Again, it's a German word, and the German scientists gave a law, Paschen's law. We had, again, it is valid, it is derived for uniform field electrode systems of very small gap distance. It has been verified later. In fact, Parsons derived it for uniform field electrode systems for very small gap distance, but for slightly longer gap distance when the field is no more uniform, but still the field remains within weakly non-uniform field configuration. This law has been verified. That means it is applicable for uniform field configuration as well as also for weakly non-uniform field configuration. Only the mathematical derivation is slightly different. So let's begin with the Parsons theory, which originally he gave. The weakly non-uniform field concept itself came later, and people did derive, worked on weakly non-uniform field later. So let's first try to learn the Parsons law. Original Parsons law accomplished in uniform field electrode system. So Townsend's criterion for breakdown, we have learned, that is gamma E alpha d minus 1 is equal to 1. So if we, in this equation, we can also write, this equation we can also write alpha d is equal to ln 1 by gamma plus 1. And alpha, we have also learned that alpha, this should be alpha here. No, it's wrongly printed here. Alpha and gamma, this should be gamma here, not lambda. Where the coefficients alpha and gamma are functions of E by P and are as follows. There was another, this is followed for electropositive gases. This has been derived for electropositive gases, but it has been also verified for electronegative gases. Mind it, that electropositive, we consider the atmospheric air to be electropositive because the oxygen content is, oxygen is a very weakly electronegative gas. So we consider air to be an electropositive gas, but it has been verified in other gases also. And later it has been also verified for electronegative gases when the use of SF6 gas, which is a purely electronegative gas, increased. Alpha here can be given is a function of E naught by P. So alpha is given as P function 1 F1 E naught by P, and gamma, another function, F2 E by P in this case. And we can also write when we are trying to uh, derive an equation for the breakdown in uniform field, EB, the breakdown field intensity required in uniform field, will be equal to UB, that is the potential UB applied upon the gap distance because of the uniform field. EB will be equal to UB by D. When you put these alpha, gamma, and EB value is equal to EB to be equal to UB by D, and for breakdown, when we are trying to find out the breakdown voltage, the breakdown field intensity is being written here. This equation was given by Paschen. What do we conclude from this equation? Paschen found experimentally that breakdown voltage depends upon the product of gas pressure and inter-electrode spacing for uniform fields. So the previous equation in the previous slide, as you can see the previous equation in the slide, this equation in the slide, you have the pressure, the gap distance, and the breakdown voltage, isn't it? So you can say the breakdown voltage is a function of pressure and the gap distance between the two electrodes. So this is known as Paschen's law. The scientist Paschen established this experimentally way back. Can you imagine? In 1889, from the measurement of breakdown voltage in air, carbon dioxide as well as hydrogen, not just atmospheric air. It can be shown that this law is also applicable for electronegative gases, as I mentioned. The values of alpha depend upon the particular gas and of also upon the electrode material. The value alpha would be dependent upon the gas as well as the material you've taken, because you can imagine in this breakdown process, gamma process is also taking place, because the experimental work and this validity was done only for very small gap distances where the gamma process plays a role. And as you increase the gap distance, the gamma process diminishes. That means the role of the electrode diminishes when you increase the gap distance. The breakdown voltage of a gas in uniform field is therefore a unique function of the product of gas pressure P and the gap distance of the electrode D for a given electrode material and its conditions. So as we go to the next slide, so this is on the figure on the left side. It is a schematic drawn taking breakdown voltage as a function of PD, the multiplication of pressure and the gap distance for uniform field electrode system. So very typical breakdown characteristics measured. Let's consider this if the D is considered to be constant. That means constant gap distance is maintained between the uniform field electrode system. Only thing, you begin with a high pressure. This is P high, as you could see. When you have very high pressure of the gas, the breakdown voltage is here. And when you reduce the pressure, the breakdown voltage also reduces, and there is a minimum. And when you continue to reduce the pressure. That means when you continue to reduce the pressure, that means you land into vacuum situation. The air density goes down and vacuum is achieved. Once again, the breakdown voltage starts increasing. We all know that at high pressure, the breakdown strength of any gas is very high, and also the breakdown strength is high for very low pressure, that is in vacuum. One can explain this curve in the way, as you decrease the pressure here, the breakdown voltage decreases. Why? An electron makes fewer impact ionization because the density of the gas decreases at lower pressure. The probability of an electron to make impact ionization reduces because of the lower density of the gas. And the lower voltage for breakdown is measured because when it makes lesser number of impact ionization, there is lesser loss of energy in the gap, and the energy is gained only from the application of the voltage. So even at lower voltage, the breakdown can be measured, and that is how you reduce the breakdown voltage to this is the point, the minimum point is somewhere very close to atmospheric pressure. We have analyzed that also very well. You may read in the books. And then we create vacuum. When vacuum is created, the probability of an electron making impact ionization, which is required for the breakdown to be achieved, goes again low. Now, how can you force an electron to make more of impact ionization? The only way is to increase its potential energy, its kinetic energy, for which higher voltage is required to accomplish the breakdown. I mean, you increase the voltage in this region when in the vacuum to increase the probability of an electron making more successful, more elastic impact ionization to produce the required number of charged particles needed for the breakdown to be achieved. As you can see it here, very interesting. This was the schematic explanation, and people have measured this curve here. This is a Parsons curve for air at temperature 20. So these are, you can say the dot are the calculated values, and these circles are the measured values, and they very much are the same. As you can see, the calculated values by Parsons law and the measured results are the same. This is a very interesting phenomenon which has been observed. So we will talk about the further work in this field in the next lecture, and let's finish it here. The time is up. So we'll talk further in the next lecture. Thank you very much.